trickiest part, I guess, is like to know use depending on like there's it's the first time you class. So there's like digital discussions that we
So let's get started. We will try to wrap up our study of data structures by going over hash tables and DQs, and then we will start our segment on graphs. We will begin by basic definitions, and then we will move on to breadth first search, talking about graph traversals, and so on. So, last class we talked about hash tables. We started talking about hash tables, and if you recall, the setup of the hash table is you have a universe of elements. And think of this universe as vast. It's much bigger than the set of elements you actually want to manage. So this universe could be running in trillions. I mean, the size of the universe could be all possible 128-bit integers or anything like that. So these are really, this universe is very large, but you're storing a large set inside that. So S is a subset of the universe, which is of size n. And you want to store this in your hash table. Of course, this set is often dynamic. So you want to be able to add to this set, subtract from this set, remove from this set, search for something. So the only operations that a hash table effectively performs is an insert procedure, a delete procedure, and a search procedure. And the key idea of a hash table is that you build an array of size roughly n, which roughly corresponds, is proportional to the number of elements you expect. Of course, this number n could actually be changing. And so sometimes you might adjust the size of your hash table, but generally if n is going to be always between a billion elements to 2 billion elements, then your hash table would be of size roughly 2 billion. Sometimes you will keep the hash table to be a little larger, and we will see how it will come in. But you would say the hash table is of size m, and m, so that's the size of the table. And there is a function h that takes any element of u and maps it to an element in 1 through m, or 0 through m minus 1. So that h is a function that maps u to zero through m minus 1. Okay, that's your hash function. And the idea is you simply, if you're trying to insert an element x, well, that's simply store x in t edge. Search x, search equal element in x, look for x in t. Delete x. If search x returns true, see. Look for x. X, if it's in there, delete. Okay, so I've written this a little roughly because the exact details depend upon how things are stored inside. As we discussed, one of the aspects of a hash function is it cannot possibly u is the size of the universe is much bigger than n, which is approximately the same as that. So it is much bigger than n. So it's impossible to have every element in U have its own slot. It doesn't make sense. And if you try to build a hash table at the same size of U, there will be multiple problems. A, there will be a problem of storage. B, if you try to compact your storage, then effectively there will be a problem of time. Okay, you should think about it. Why? Okay. So basically, you cannot avoid many elements from U mapping to the same location in H. It's impossible to avoid. Okay? That's exactly what is referred to as a collision. So it basically is a collision, and how do you deal with collision? There are many ways to deal with collision. One way to deal with collision is called chaining. And by chaining, what happens is you have multiple elements, you just chain them in a linked list. Okay? If it's empty, then you just put an empty list, otherwise you just add a list. Okay? We went through all of this last time. Okay. So the thing to observe is a running time of any of these operations, insert, search, or delete, is essentially proportional to the length of the chain. Okay? So running time is something like theta of the length of the chain. This is not a very well written statement because the length of the chain, of course, varies from slot to slot. But you could say that, okay, the running time is theta, the largest length of the chain. Okay? But then again, if you're very unlucky, then the length of the chain could be very large. All the elements that we happen to add all fall into the same slot. But we will observe that those things are very unlikely. But let's try to understand. So, running time of the length of the chain. So our main goal is to keep the length of the chain short. So this is, so what we're going to show is that if a hash function is chosen well, the expected maximum, expected length of the chain is right on. Is just a constant. Okay? Theta 1 means just a constant, independent of your size of element. Okay? So, let's try to think about it. Remember that we do not know what elements we are going to put in there in the list. If we knew which elements we were going to put in the list, then we might figure out, oh, I'm going to map this element in this location, this element in this location, and so on. But we have no idea what the elements are. Okay, that we are going to put in. So, what would be an ideal hash function? Is a question that comes to mind. I just want to be able to make sure that no matter what set of elements you give, I spread them out as evenly as possible. Okay? So what do you think would be an ideal hash function without knowledge of the elements? Now, you might say, okay, these are integers. I'm going to take a look at the first 10 bits. If this is 2 to the 10, then I'm going to look at the first 10 bits. Okay? The problem is, moment you tell me what that function is, I can give you an input that will make sure that many elements map to the same location. You agree? So if you just go to look at the first 10 bits of your integers, then I will just give you all the elements that share the same first 10 bits. And you're going to put all of them into the same. Okay? Any other ideas you can do? Yeah?
I think we can do the modulo.
Okay, you can do the remainder.
Yeah.
A remainder is like the last 10 bits. If you think about it. A remainder of a number mod something. It's not exactly, if it's mod something to the power of 2, then it's the last 10 bits. If it's not something to the power of 2, like it's a modulo of prime, then, so let's say we pick, let's say we say h is equal to h of x equals x mod m. This is a very clean hash function. Okay, very good, good idea. So this gives you a number between 0 and m minus 1. Okay, and everybody agrees that this will give you a number here to here, and then you right? What's the problem with this?
Too many collisions.
It could have too many collisions when? If the numbers are all, for example, multiples of m. If every number is a multiple of m, then what will happen? Everybody collide at location 0. Right? Okay, everything is a multiple of m, then h of x would be 0. So, and there are lots of multiples of m, right? Because remember, the universe itself is huge. So there are lots and lots of them. Okay, so, but of course, I'm trying to come up with these sort of adversarial. You give me a hash function, I tell you a bad input. You give me a hash function, I tell you. So of course, any hash function you give me, if I look at it, I can tell you a bad input for that. Unavoidable, because we know there are lots and lots of elements in the So the hash function you're going to design needs to have randomness, which I am not aware of as an adversary. Okay, that's the minimum. So that's absolutely, so anytime you design an algorithm using hash functions, that is a randomized algorithm, because it is relying on some randomness behind it. Okay, even for that hash function, which chooses things randomly, there is a worst case input, but it's so unlikely, and even an adversary who knows about your hash function, who does not know about your random bits, cannot select that input because it's so unlikely. Okay? We will do a little bit of the analysis. We may not do it fully for you to appreciate completely the value of randomness, but you'll see. Okay. So, for example, what we could do in this case is instead of x mod p, we could choose, sorry, instead of x mod n, we could choose x mod p, where p is a random prime in a certain range. Let's say in m into n. This is not a great idea because there are not that many primes in this range. Not necessarily that many primes, but certainly that's a possibility. So there you add some randomness. Okay. Now this would result in numbers that are bigger than m, possibly, because p is a larger prime. So you might do another mod m to bring it down to this region. Okay. Whether it works well or not, it's not completely clear, but that's a possibility. Let's say we have complete randomness available to us, whatever we could do. So then what an ideal hash function could be is the following. What it does is so we could have done we could do an ideal hash function, and an ideal hash function is the following. H x, it returns a random location For every single element, at the beginning itself, it chooses a random location in 0 to n-1 and places it there. Okay? Yes?
Shouldn't there be like, it should like, but then if you choose H of S's, S mod P and then mod M,
Yeah.
P is always random selection every single time. How do you guarantee reproducibility?
No, it's good. You cannot choose P randomly every single time. This is all done once. In the definition of H,
So you choose the same P
Every single time.
X in there.
exactly. Okay? Similarly here, you're going to choose a random location once at the very beginning. For every element in the universe, you choose a random location once at the very beginning, and that's what you're going to use forever. Because as you point out, you cannot keep reusing randomness because it doesn't make sense. You first put it in some location, and then you change your randomness. You don't find it anymore, right? So you have to use the same randomness. Okay? Okay. So let's try to see how good this hash function is. So let's try. So the main thing you want to understand is the chain length, right? The chain length is basically a function of collisions. So let's try to understand collisions. Okay? So what is the probability that we pick a particular location and find out that there is a collision? Okay? So let's pick any location I, location L. Let's do the following. What's the probability, let's calculate some things, that hx equals hy, where x is not equal to y? What's the probability that h of x equals h of y? So, okay, we started talking about probabilistic things when we solved a very elementary probability when we did randomized selection. So let's review some of these things. So the probability that these two are the same is you first. How many different values can h of x take? And different values. So the way you can write it, there are many. I'm going to write it a slightly more elaborate way. There is a simpler way of seeing this, but so this is the sum over all possible choices of h of x. So let's go locations from 0 to n-1. Probability that h of x equals L and h of y equals L. Do you agree? What is the probability that h of x equals L and h of y equals L? We said that we're going to pick a random location. I didn't explicitly say that, but I have to say that this randomness is done independently for every single element. So this is being done uniformly and independently. So the probability that h of x equals L is 1 over m. Probability h of y is equal to L is 1 over m. Since this is an AND of two independent events, so the probability of the AND is the product. Okay. So this is equal to summation L equal to 0 to m minus 1, 1 over m times 1 over m. Okay? So what is this equal to? Right. So the probability that h of x is identical to h of y is 1 over. So probably the two things will collide is 1 over. Okay. Question?
Is it 1 over m squared?
Well, but we're adding it up from LO 0 to m minus 1. Okay. Times that. Good. Okay. So that's the probability there. Okay. So now, what is the probability that there is a collision at a particular location? Okay, so we can pick a particular location. If you found that we can find out what is the probability that there is a collision at a particular location, or what is the expected number of elements that map to a particular location. We can calculate that too. So that's the probability of collision. Let's look at the length of a chain. At location L. How do you calculate the length of a chain at location L? Well, let's calculate the number of elements that will map to this location L. So there are again n elements. Remember, that's fine. So remember there are n elements which you are trying to map. Okay. Let me say xi equals 1 if I or x the h of I equals 1. Write this as x. Okay. X of I is a random variable. I say that it's 1 if h of that element I maps to I. It's 0 otherwise. Okay. I is an element in F. Okay. So what is summation xi? What is xi? Xi is 1 if I maps to location I. Then what is summation of xi over all I belongs to S? That's the number of elements that map to S. So that's exactly the length of the chain. Okay? That's exactly the length of the chain. So let me call this variable, let's say x for now. So the expected length of the chain, this is the expected length of the chain. Okay? The expected length of the chain is nothing but the expectation of the sum of these variables. Okay? Clear? And one of the crucial things in probability that you should always remember is that the expectation of a sum of random variables is exactly the same as the sum of the expectation of the random variables. It is equal to summation expectation of xi I belongs to. Okay, why is this? Because calculating the expectation of xi, why is this useful? Because calculating the expectation of xi is very straightforward. Let's calculate that right now. But until that point, it's clear. Right? So expectation of x is equal to expectation of. What is the expectation of xi? Well, it only takes two values. So there are only two possibilities. Expectation of xi is equal to 1 times probability that I maps to L. Hi equals L plus 0 times probability that's Hi not equals 1. Right? The expectation of a variable is the value it can take multiplied by the probability it can take that value. So the expectation of xi is 1 times the probability that its hi is equal to L plus 0 times the probability that hi is not equal to L. What is the probability that hi is equal to L? 1 over m. So what is the expectation of x sub I? 1 over n, because 0 times anything is 0, plus 1 over n. Okay? So, regardless of what I is, regardless of what L is, expectation of that xi is 1 over n. So this is 1 over n. So what is this equal to? Summation over all I belong to S of 1 over n. So what is this equal to? N over m. The number of elements in S is n. So the expected length of a chain is n over m. N over m is referred to as the load of the hash function. How many elements are you putting in as a function of the size of your table? So the smaller you make n, the larger the load. The larger you make n, the smaller the load. Okay? So that's sometimes referred to as alpha, which is the load equals n over. Okay? Any questions so far? Now, we didn't go through this, but it turns out that if you choose your hash function randomly, then the probability that the length of the chain would be much bigger than this is very, very small. Okay? So this is just the expectation. Expectation is like the average length of the chain. But it turns out that the length of the chain, even not just the average, but the length of the chain is so concentrated around this that you can assume that the length of the chain is very close to this. Okay? It can be shown that the high probability chain length is big O. Okay. You will have to put some constant here or add some other error there, but basically it's very close to. Okay. And not being precise here, but for a precise statement you would need certain kinds of concentration bounds, which we are not talking about here. Okay? All right? Okay, so we got this. So we got n over m, we got the expectation of x. So now let's go back to our calculation. So the running time of insert, search, and delete is related to the length of the chain. Okay? And actually, to be really precise, I should have written there length of the chain, meaning even if the length of the chain is 0, it takes you at least one time to look at it. So to be really precise, I should have written as the running time to be 1 plus the length of the chain. Okay. So let me just write that down here. Run time is theta of 1 plus the length of the chain. And the length of the chain now we have determined on expectation is the average, the load. So if you set your m to be something like 2 times n, so if n is of the order of n, then we obtain that this is nothing but a constant. Equals theta 1 for our choice of n. If you choose your n to be very small, like if you choose n to be much smaller than n, this will increase the runtime. If you choose your n to be much bigger than n, then it will bring this down sharply, but of course it will take you 1 unit of time anyway to look at it, so it's not going to have a huge impact on the runtime. Okay, so that is the motivation behind using hash functions. Let's get back to our understanding of this random hash function. So let's suppose we had this random hash function that kept track of this random location for every for every x belongs to S. Apply that. What is the problem with this approach? It has a very good performance in terms of its collisions and length of chain and so on, but there is a problem with this approach. Pardon? Memory for? Well, no, the hash table is of size n, which we said we could keep it to be close to n. Pardon? No, because the chain length we decided, we have agreed the chain length is no more than alpha, which is roughly a constant, so chain length is also small.
You have to know every element in the universe before hashing it.
Sort of, you're right. You have to know every element in the universe, but that's okay. I mean, if I tell you that it's a 128-bit integer, then you know every element in the universe implicitly. So in that sense, it's not a bad thing. Yeah?
Is it because they're using a random hash function in that, like, we're just randomly assigned here, so like, your lookup might be a little more difficult?
So the question is, how will this hash function be computed? Okay? How are we going to compute this hash function? If somebody gives you an element, how are we going to compute it? I said, a priori, I'll choose a random number for every element. Okay? But if I'm going to choose a random number for every element, as we discussed, we have to use the same random number again, or whatever you're doing. But what do we do? How do we keep track of it? In order to keep track of it, I have to store it. Well, I'm now storing the entire universe, the random number for the entire universe somewhere. Okay? This is similar to the problem alluded to earlier. So the problem is that this hash function is not computable in some way. I mean, how can you even compute it efficiently? So the whole study of hash tables, hashing, and so on is focused on trying to construct hash functions that look more and more like this. They won't, of course, they will never achieve the complete randomness that this achieves, but they will have more and more properties like this. Yes?
Wouldn't P being random be a problem sometimes? It's too small or too large? Really
Well, P is being chosen between m and 2m in that example. So by the way, that's not necessarily a good hash function, but I'm just saying that that's a possible one. But then, if you were choosing it, you would choose it between m and 2m. But you're right, you don't want your P, if you're going to do a mod, there is mod often done. If you're going to do a modular arithmetic, you would choose your primes, whatever numbers, much large numbers, so that you get enough randomness. Okay, so that's the ideal hash function. We just So let me just give you an example of a hash function. So here is the hash function that goes. So let's suppose your table, again, remember your H is trying to map the universe to a number between 0 and 1. So what you do is, if you have an element from the universe X, you view it or represent it as in base, as a base m integer. Okay, so what that means is you write it as, let's say, xk, b minus 1, b minus 2, x 0. Each of these itself is a number between 0 and n minus 1. Okay. We know that we can change bases, right? We can change base from binary to base 3 to base 16 to any base that we want. So we are going to, and every element of u is nothing but an integer. It's written in some let's say sequence of bits. And so we will take that u and write it as a base m integer. Okay, so it has these many. So imagine it's something similar to. So let's say if m was a power of 2, it will be something similar to taking those bits and then breaking them into blocks, okay, which would be perfectly fine. And then what you do is you select k random numbers. K random numbers in A1, A0, A1, A, or K plus 1 random numbers. And then you set h of x to be summation I equal to 0 to j equal to 0 to k ai times xi okay. So you take a number a0 multiplied by x0, okay, plus a1 times x1 plus a2 times x2, but all of this we do in modulo m. Okay, and we choose your m, and we often choose m itself to be a prime, or a suitable number. There are other choices you can also make, but m is a prime number in the range that's bigger than n. Let's say in the range n to 2. Okay. This is an example of what is called the universal hash function. Has the same properties of collision and expected chain length as ideal hash function. Okay, has the same properties of collision and expected chain length as ideal hash function, and it has very similar properties in terms of this high probability bound that I mentioned, but of course it can't match it completely because that one is truly random, while here this randomness is shared. The amount of randomness here is much less than the amount of randomness there. Okay, and notice that calculating this is very efficient, right? Why is this calculating very efficient? Well, all we did was, the only thing we have to store is k random numbers. How large is k? Well, k is as large as the number of bits in u divided by the number of bits in m. Okay, what is the size of k? K is the number of bits needed in u. The number of bits needed in u, if you're thinking of u as basically a set of integers, the number of bits needed in u is log of u divided by log of m. So k is, even though u and m are pretty small, Log u is very small. Log u over log n is small. Sorry, u and u is very large. Log u over log n is very small. So these are the only elements that you need to store, and you are doing this randomness once at the beginning. That's all you need to store. And calculating the hash function is not difficult. It's just some multiplications and some additions and mod operation. Okay. So now this is not the only hash function that is used. There are lots of choices of hash functions that are and hash functions are heavily used in cryptography, because the value of a hash function is you can calculate it efficiently. Inverting it is almost impossible or very inefficient too. So intractable. So hash functions, there is a huge study about what kind of hash functions you should choose in different circumstances. This is just one example of something that achieves similar to what we want to achieve. Okay? Any questions? So we are not going to look into details of these hash functions. For our purposes, they exist, and for our purposes, there is a way to ensure that the running time, expected running time, is constant. Expected time for the insert, delete, search operations. Okay. Yes.
So you say m equal to prime number in range n to 2n. So the n is the size of the universe?
No. N is the size of the set that you are trying to store at any point of time. N is, so this is for an application. So remember, U, so N is the size of S. Okay? N is the size of S. So there are three things. There is U, which is the universe. S is a set that is changing with time, but you believe it's going to have something like n elements in it. So you don't have, n is not a very accurate number.
So how about this? So this time I try to process this S.
Yeah.
How about next time I process another S?
Very good question. So if S is going to dramatically change over time,
And then
then notice that when you say this time I'm going to process this S, next time I'm going to process a different S.
Yeah.
If you mean that if you're the set, so you're using a hash table to store S, and now you have a different S. If that S is substantially different from the first S, then these are different problems. The whole point about hashing is it's only useful if you're going to look at the same elements again and again. If you're not going to look at the same elements again and again, then you might as well have a different storage for them, right? So the most useful applications are where you have an S that is not fixed in time. It changes, it increases, it decreases, it increases, it decreases. Think of n as maybe the largest size it can ever take. Think of that as n. If you're using it for S that is decreasing, increasing, and so on, then suddenly it is increasing significantly, then it's probably better to rehash. Then you would
use a new hash
then you will probably do a new hash function
based on the large size.
Based on the larger table.
So I remember you said the draw points for the way we talked before. You said we have to decide the size of the universe first, and then
No, size of the table. Well, no. So the universe is given to us. We don't have any control on that. Okay. So
but the size of the table, we already know that, right? It's m. We know it's m.
No, that's what we are deciding. So in order for our what we don't have control on is in the size of the universe, right? We don't have any control on the size of the set S, because it's going to come and go with some number n. So we know the universe. We have an estimate for n. We have to choose n. Once we choose n, we have to choose our hash function. Okay? So the general rule is m is roughly close to n. N, 2n, 3n, some number like that. And your hash function, you can do whatever you want to do with it. Okay? So here m is the prime number in the range n to 2m. Okay, and by the way, this is just a rough estimate. You could have picked it bigger than 2m. So that's what m is. Okay, and the universe is whatever it is. Okay, it's some large universe, much bigger than m, much bigger than n.
Then why the hash function way to before is not so good at this in that one?
Oh, between this and this one?
Yeah.
Well, it's just we can't, for this choice of hash function, we may not be able to prove this bound and that bound very well. We may not be able to prove this bound, for example, very well. Okay, and even if you're able to prove these two bounds, we may not be able to prove that there's very good probability is right. It's just a question of the bounds. We can prove. It will have this. It will have the property that you're always storing it in the same size and so on. But it might the guarantees it can provide for chain length and collisions are weaker than the guarantee that this can provide. Okay. So let's move on. So let's look at a different data structure which is completely deterministic, which has the value that hash functions do not always provide, that of being able to compare. So one thing to notice here is that we are viewing these as numbers and we are doing these arithmetic operations, but that's purely for deciding where to store. We are never thinking, we are not storing these elements in a particular manner. We are not storing 5 close to 6, we are not storing 15 close to 20 and so on, right? In the hash table. We are storing them in really, literally random locations. So priority queues are data structures. They're also referred to as heaps. And there are different implementations. Sometimes priority queue is referred to as an abstract data structure, and heap is a particular implementation for priority queues, but I'm going to treat both of them as the same for now. So priority queues and heap. So there also we have the same situation. We have a set S we are maintaining. Our universe here is, think of it some ordered, totally ordered set, like integers. That's the universe. The set S we are maintaining is some subset of U. And let's say n is the size of S. And the questions, the kind of operations you want to do: insert, delete, search, possibly, we'll have to see whether we can handle this or not. And one operation that we'll often use in this case is delete the smallest element. And you'll see this coming up again and again in various applications. And we can use, so these things we can do very effectively in a hash table, right? But delete min, how would you do delete min in our hash function application that we just said?
Find the minimum.
Finding the minimum one, how do you do that? You go through the entire table and look at every single element. Okay, that's a linear time operation, theta n, there are n elements. That's way too expensive if that's one of your crucial operations. Okay. So exactly which data structure you want to use for your solution really depends on what are the operations you want to run and how fast you want to run. Okay, so insert, delete, search, and delete. So this is the crucial. Whenever you see something where you are trying to look for the minimum element again and again, think about priority queues. Okay? Okay. So it's a very simple data structure. It's a completely deterministic data structure. It stores elements in a binary tree, in a form of a binary tree, and we will see in a moment how to do it. So let's take a quick example. Let's say your set S is set as is okay. So it's going to store elements in a balanced binary tree. I'm going to draw it as a binary tree, then we are going to actually see that it's very easy to maintain it as an array, where the tree is implicit. But so that these numbers, the min is always at the top. Okay. And then you always have the property that every parent value is less than equal to the value of its children. Beyond that, you don't have any particular order in which these things can be stored, but we'll maintain it as a balanced. Okay, so let's just make sure we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is an example of a heap or a priority queue. So the only thing that matters for you in this picture is it would be a balanced, and actually it's referred to as a full balanced binary tree. Okay, and value of the parent is less than equal to the value of. You agree? Does it maintains all of this? Okay. Okay. So that's the only requirement. Now let's try to see how we will quickly implement this using arrays. And second, we will try to understand how long these things will take. Okay, and then we will move on. So one way to implement this easily is a method called, it's just using arrays. So this will, our location would be, we're going to just have, let's say, h of 0. So we will store the top of the tree in h of 0, top of the heap, h of 0. This would be h of 1, h of 2. This would be h of 3 to 7. Sorry, 3 to 6. Did I get it right? 0, 1, 2, 3, 4, 6. Okay. So then, what do we have? We have that to calculate the parent, just from the index you can figure out what the parent is, right? So let's see how to do this. So the children of the right of I would be 1. parent of I? What will be the parent of I? So it could be written floor of I minus 1. There are probably other ways to write the same thing. Okay? That's clear, right? Okay. So now, once you have this, so that's right, left, parent. I. How do we? So I'm not going to go through the details. People should. There's a lot of material out there we can look over. But so let me just do a couple of examples of addition. So if you want to add a new element, let's say 17. So you're doing insert of 17 to this. What do we do? Well, we have an array H which is going from 0 to 7, where n was 7 at this point, but we've added a new element, so we have to add a location H of 8. So all we will do is add this location H of 8 and put 17 there. Okay? Notice that I'm drawing this picture as a tree, but in memory we are just storing it as an array. Okay? So we have added this H17, so we have created this array, which is a simple thing. But now we have to fix problems. And the problems we have to fix are the things that violate the heap property. This is what is called the heap property. So I have to fix the heap property violations. And how do I fix the heap property violations? By just doing a swap. So I check 17, so I've added H of 8, so I check 17 and 19. Okay. Looking up my parent just takes me constant time. So I see a problem, so I do a swap. So do a swap, and that makes this 17, 15. Then I compare this with this. Notice that once the smaller one moved here, okay, the larger one moved here. If there was something below, I don't need to check for that because originally the heap property was violated, was fine, so there is nothing to check. So 17 and 9, there is no problem, and I'm done. Okay, let's do one more example. Let's say I insert 1. So again, the next element that's going to be added is here. That's 1. What do I do? We do a swap of 1 and 15. Then we do a swap of 1 and 9. Then we do a swap of 1 and 3. We are done. Okay? So the running time of this, maintaining this heap property, is basically just wherever we added it, walk along the path to the root and do swaps if necessary. So that is basically the height of this tree. But remember, this is a completely balanced binary tree. So the height of the tree is no more than log base 2 of n, seeding of it probably, seeding of floor. So the running time of insert equals big O. If we write it as big O of log n, it's actually no more than, I think it's right there. Big O of log n. And there are situations where it can be as much as log m, so you can replace that big O by theta of log m. Clear? Okay? Okay, let's try delete. If I had to delete an element like 3, what do I do? Well, remember I have to shrink my array, right? So the way I would shrink my array is remove this. Of course, I will delete it. But I'm going to put the last element that is there in the heap and put it there. Okay? So I replace my 3 by 15. Actually, let me do a slightly different one. So let's say I'm deleting let's say I'm deleting 19, sorry, 22, and that's the same. So I'm deleting 63, sorry, deleting 20. There's no difference. So let me do the same thing all the time. So I'm deleting 3, so I move the 15 here. Yes. Now, that could create a problem. What kind of problems could it create? Could it create a problem going up? Well, this number, in this picture at least, this number is greater than this number. So it's not going to create a problem there. But it could create a problem down. Okay? And is it creating a problem down? Yes. So what do? We compare that with the minimum of the two, and put the minimum of the two up there, and swap it with this, and then try to fix the problems down. Okay. So in this case, you replace this 9. Okay. And it turns out you can follow this, that meaning in some cases it could create problems going up. Okay, you realize when will it start creating problems going up? If, for example, you are picking a number here, all these numbers could be smaller than all these numbers here, and you take a small number here and put it there. But anyway, you can figure out which it will only create a problem in one direction or the other, and you can fix it. And that will again take you time. Order log n. Okay? Yes?
Shouldn't we first find the element and then...
Good. Excellent. So, that comes to search. So, typically delete means you already know, you already have a handle to that, you have a pointer to that, and you're deleting it. Good. So, then it comes to search. Okay? So, if I'm searching for an element, how do I search for the element? Yeah?
Start at the top and you have to do comparisons.
With what?
So, because you know the numbers are always increasing as you go down.
Yes.
So then you can decide which
So,
branch.
okay,
to
so
search.
let's try. So let's say I have the number 31. Of course, which direction do I go?
Then you have to go.
Both directions. And then I have to go both directions. So search could take as much as linear time. So heap is not designed for search. So heap is okay with delete only if you give a handle to it. Okay? So search could take you as much as data and time. There is nothing you can do about it. Notice that this is different from something like a balanced binary search tree, where things are ordered. Again, here also things are ordered, but in a different way. The way things are ordered here are optimized for something not exactly delete min, but it's optimized for the operation find min. How long will it take you to find the minimum? 1 unit time. You just have to look at h of 0. That's what it is optimized for. Okay? So search will take theta n, find min will take theta 1. And what about extract min or delete min? Delete min will require you to look this up and delete it. But deletion would mean you move something from here to the top and then fix it. And that will take possibly log n time. So delete min will also take log n.
why can't you just move the minimum of the child nodes there instead of the leaf node? Because anyway you're comparing that.
Yeah,
again.
but then you'll have to move it there, but then you have to fix that too.
Yeah, but that we don't have to put the last.
So let's try to understand that. So let's say the minimum happened to be here. You'll put that here. Then the minimum happened to be here. You'll put that here. Then it creates a hole here. Now your heap has a hole. So it's very important. If you're deleting something, you have to free up the last cell because you're storing it as an array. If you're storing it as a different construct, you might be able to do something else. But if you're storing it as an array, which is very simple, you will have to move the. Any other questions? Okay, good.
Could you explain again why delete is overblocked?
So the delete, the way we do deletes is we blank that out, okay?
Or you have to shift it?
And we move the last one element here. That creates a problem either down or up, and we try to fix it either going up or going down. Okay? And the number of comparisons you have to swaps you have to do is essentially length of.
But then, if you just give a value, like say, if I say delete 22, I have to search for 22.
No. Delete, right, that was the question earlier. When I say delete, I won't say delete 22, I'll tell you a given node. I'll give you a point. I will already have found 22 and I'll want to delete that. If you have to search for it, then it cannot take linear time. It doesn't really take linear time. Yeah?
Going back to his question,
Yeah.
what's the problem with choosing the minimum of the children to replace after the deletion?
So you choose the minimum of the children. So let's say you remove, let's say this number, okay, take this 22, take the minimum of 37 and 46 and put it here. Then your array, if you're storing it as an array, you have elements in location 0, 1, 2, 3, 4. 5 is an empty slot. Now you're not storing it as an array, you're storing it as an array with some empty slots. Then, if you add something here and here, now you have parents which are not defined. Remember, if you're removing this, then your tree is not, actually it's not a complete binary tree even. You've removed this element. Now the tree looks like this, and then it may not even be balanced, depending upon what you do over time. There's no more questions? Yeah.
Could you repeat why the running time insert and delete is beta log n and not theta log n?
You could put theta log n. Absolutely. Yeah. So, I'll emphasize the following thing. What does this mean? This means that for every insert, the running time is at most C log n.
Right.
And there exists, given a heap, there exists a thing you could ask to insert that could take as much as that time. Of course, some of the other inserts could take less than that time, right? Because if you're adding an element that was really large and you're adding it to the bottom of the heap, nothing will change. You don't have to do anything. Okay, so we are done with these data structures, and these data structures will come very handy when we start doing yeah.
We didn't talk about how to create this.
Good. That's a good, very good one. Yeah. One way to create this heap is you could do a sequence of inserts. So as you're adding that, you can do a sequence of inserts. But there are other better ways to do it. I'll talk about it. So me write down here. So how do you build? So if you have a set S that you started off with, just like in a hash table, if I want to store them in a hash table, I could just keep inserting the elements into the hash table. Similarly here, I could just keep inserting. Repeated calls to insert. That's one option. The second option, which is just a smarter way of doing it, which basically would store all the elements in an array, but then repeatedly fix this by fill the elements in the array and repeatedly fix key property violations. I'm not going to go over this. This can be done you just have to follow the logic of how to do it. So you start with the largest element, then you see whether there is any violations at the top of the heap. So if there are violations, then you fix it. Then you go down to the next level, you fix the violations, then you go down to the next level, you fix the violations, then you go down to the next level, and so on. And this can be done in linear. You can build your heap in linear time. Okay, so let's go on to a quick study introduction to graphs. To some extent, we already talked about graphs. Yes.
Question about
Yeah.
you're inserting an element in linear time.
Yeah.
Not like sorting it.
No. Good question. Very good question. So let's try to understand the question. If you are being able to insert n elements in linear time, notice that we are not exactly we built this heap and we put it together, and now we want to output the sorted sets. So what do? You look at the minimum, which you can find in very quickly. But if you have to remove it, that takes you log n time. Okay. Then you find the next minimum. That's fast. But to remove it, it takes you log n time. So effectively, it takes you log n time. Of course, n is decreasing over time. But even if you take the log n's as n decreases and add them over n, it will come out to be n log n. And that is exactly what heap sort does. But in fact, now we have talked about it, that's the heap sort algorithm. The heap sort algorithm is take all the elements, put them in a heap, and repeatedly remove the minimum. And that's heap sort. Build, but remember, delete min is take our log n time. So heap sort equals build heap plus repeated deletions. Okay, plus n deletions. Okay, so graphs are structures, or combinatorial structures, which I have represented as this. This is set of vertices. This is set of edges. E is a set of edges, B is a set of vertices. And they are all over, they arise in many different scenarios. There is a whole field of graph theory which has been around for multiple centuries in study of these graphs. There is a relatively modern area of network science, which is the study of graphs that arise in many applications. We have a whole institute in network science at Northeastern. We have programs in network science. There are companies that are sort of mostly building graph databases, and most of the major information and media companies operate on graphs all the time. Okay? There are lots and lots of examples of graphs. What is a graph is just captured by the vertices, also sometimes referred to as nodes, and how they are connected by edges, also sometimes referred to as links. And we will distinguish between undirected and directed graphs. Okay. And we will draw pictures like these. So this is a graph with 7 vertices and 10 edges. And these are names of the vertices. So the set V is A through G. And the set E is the edges, the set of edges. And the set of edges, we will often write it as pairs. ED, AC, ED. Okay? And we could, so this is for undirected. This is an example of an undirected graph. In a directed graph, the edge would have a certain meaning, that it is going from the first element to the second element. In an undirected graph, the edges could be thought of as vertices. Okay? Okay, so this is very standard structure. There are lots and lots of examples of graphs. There is the internet is, of course, one of the biggest examples. World Wide Web is an example. Any social network is an example. Any transportation network is an example. Protein networks is an example. And they arise, and we'll go over so many different examples in class where you might not think of something as a graph, but once you try to understand relationships between different entities, you will want to capture it as a graph. Okay, so what we would be interested in this class would be understanding, answering questions about graphs, being able to traverse these graphs, and being able to do processing of these graphs as effectively as we can. Okay, so we want to have some idea about, let's look at some sort of minimum ideas that we want to develop. So let's try to understand how to represent and store. So we talked about representation and storage. And let's some other important structures, substructures of graphs. So first, representation and storage. So we will often use n as the number of vertices in the graph, and n as the number of edges. Okay. So one question is, how do we go about storing these graphs in your program? How do you go about storing these graphs? Well, there are two very natural ways of doing it. One is what's called an adjacency matrix representation, and the other is an adjacency list representation. An adjacency matrix representation in this situation would basically number all the vertices from, let's say, 1 through 7, and then it will have a 7 cross 7 matrix. Okay? And then these would be all 0. There is no edge from a vertex to itself in this picture at least. And then you will add an edge. So A is 1, B is 2, C is 3. So there is an edge between A and B. So there is an edge between 1 and 2. And the same edge is also there between 2 and 1. There is an edge between A and C. There is an edge between C and 1. There is an edge between B and D. And so you get the idea. So you have an entry in the matrix whenever the corresponding edge exists. Okay? Good. How much storage do we need for this? N times n, which is n squared, and you can be compact and you can store it as n squared bits. Okay, if you can make use of bit vectors and so on, but it's basically n squared storage. What if I have to find out whether a particular edge exists? How long does it take? Constant time. I just have to look up. If I have to find out all the edges that are adjacent to a particular vertex, how long does that take? N. Okay, so let's look at those two things. So looking at a particular edge is just constant. Looking up all the edges of a particular vertex, I'll have to go through the entire row. Right? Okay. Okay, any questions? The other mechanism of storing the same graph is what is called an adjacency list. This mechanism works like this. You would have a list where the list will contain the name of the node, okay, and maybe other information that you want to store. So think of each of these records storing an object, but it also has a linked list, and the linked list lists all the adjacent vertices. Okay, so here it will list A has B and C, B has A, C, and D, and you could store it as a double integer, it doesn't matter. And by the way, when I'm writing it as B, I could essentially have a pointer or a reference to this, so that I can quickly use that. If we do one more, G has D and F. Okay? All right. If I have to determine whether a particular edge exists, how long does that take? It takes, if I want to find out whether DE exists, I have to look up D, I have to go through the adjacency list of D, as much as theta n, certainly as much as the number of edges that D requires, that D already has. If I have to find out all the edges of D, theta n. I just have to walk through all this. Okay, what about the storage? So, well, this is n. And what about all these? Well, there is at most n for each of them. So, okay, of course n squared. But it's more compact in some sense, in the sense that if there are very few edges, then the number of entries here is just twice the number of edges. You see that? Because each edge appears twice. So the size of adjacency list representation is usually thought of as n plus n, or theta n plus n. People see that? So in general, the way you should think about these two is, if you have a very dense graph, and what is the maximum number of edges a graph can have? N choose 2. Okay? If you have directed graphs, then it can be n squared, and if you're allowing loops and so on, it can be n squared. But basically it's quadratic in n, unless you're allowing repeated edges. So it's quadratic in n. So if you have a very dense graph, then m is very close to n squared, so there is no difference between these two. This is also n squared than n. But if it's a sparse graph, then this is. So storage-wise, this is always a better choice. Okay? Yes?
Can we do, is there like, are these representations only talking about undirected graph? Is there a
No,
difference if
no.
we use,
You can use it for directed as well.
so like say if you use adjacency list for directed, you will only store the one that they have an edge going out towards it or something like that?
That's true. You will. So if you have an adjacency, if you have, let's say this was an edge B to E, then Q to E will store a 1, but 5 to 2 will store a 0.
Okay.
In adjacency list, you will have B to E, but you won't have P.
Yes.
Okay? So, adjacency list is more efficient in terms of space, and I think the biggest value for the adjacency matrix is if you're repeatedly going to check, oh, does this edge exist, does this edge exist, and so on, then it's much better to use adjacency matrix. In our class, for most of this class, we will assume an adjacency list representation. Mostly, unless otherwise specified. For some problems, especially the ones that are going to take more than quadratic time, it doesn't matter. Okay, then you could go ahead and choose this. Depends upon the problem. For some problems, we will find adjacency matrix more useful, like all pairs, shortest paths, and things like that, and we'll go with that. Okay, good. So let me introduce a couple of more notations or definitions. Something that we have implicitly seen already: notion of a tree, okay, and notion of a connected graph. We say that a graph is connected if there is a path between any two vertices. So let's focus our attention on undirected graphs. So let's assume undirected. In an undirected graph, G is connected if for every pair, for every vertices U and V, there is a path from U to V. Notice that this is undirected, so I could have very well have said a path between U and V. It doesn't matter. And connected really means a path. It does not mean that they have to be right next to each other. Okay? So this is an example of a connected graph. This is an example of a connected graph. But if I had something like these added to them, then this whole graph is not connected. It has two connected components. Okay? Good. A tree, a graph is a tree if it is connected, okay, and it has no cycles. Okay? T is a graph okay, so tree is a connected graph with no cycles, and it's a good exercise to try to prove. And you can prove it by induction, you can also prove it by many different ways, that a tree over n vertices has always n minus 1 edges. Always. Okay. If you have any graph that has more than n, if you have n vertices and more than n minus 1 edges, it is bound to have a cycle. Okay. So a tree over n vertices has exactly has n minus 1 edges. If a tree over n vertices has n minus 1 edge, if a graph over n vertices has n minus 1 edges and is connected, then it has to be true. This is really a worthwhile thing to try to prove yourself by induction. Okay, I think I'll stop here because we're starting a new unit in time. So just a couple of reminders. So we have midterm on Friday. Again, location will be sent out by Yota and I'll announce it next on Friday's class. Midterm Friday 8 p.m. It will include all material that was covered in the first, second, and third problem set. So basically, everything. It does not include hash tables that we covered today, and everything that we covered until last week. And there will be review sessions. So we are going to use the recitations for the reviews. So you can assume a review on Wednesday and the 2 Thursdays. So the review will be on Wednesday. And I will post all the review problems. I'll post the problems by Wednesday. Okay? Okay. I'll stop here.